Good morning, physics class, and welcome to problem set 36, day 2. This week, we're going to be looking at stuff to help you get ready for the test this week. It's the 36th week, so you'll be having a test. So just kind of keep that in mind as we continue down this road and as we work on some of this stuff. All right, the first thing that we're going to face today is a power problem, an electricity problem. So it says you have a 48 volt battery. So we have our 48 volt battery, and it is connected to a 16 ohm resistor, and it asks how much current flows through the circuit. Well, we know that V equals IR, volts equals amps times ohms. That's usually how I try and remember it. So we got 48 volts. Excuse me, let me fix that. 48 volts equals, we don't know how many amps, times 16 ohms. So we do 48 divided by 16, and we'll get our amps equals 3 amps. All right, now the rest of the part of the problem says how much power does the battery provide? How much power does the battery provide? So we can calculate power by the equation. We could say that it's I squared R. I believe maybe we talked about this yesterday, but the equation we had yesterday is that P equals V times I. And if V equals IR, we could take and we could substitute this volt into that volt, and we could have, if we combine that, we could get P equals I times R times I, which is I squared R. That's how we derive this second equation for power. Excuse me, wrote two R's there. So power equals amp squared times R. So we know that we got 3 amps, and we have 16 ohm resistor. So we're going to do amps squared times the resistor of 16. So we'll do equals the power equals 3 squared times our 16 ohm resistor equals 144 watts. Make sense? Now, what is a watt? Well, a watt is a joule per second. A joule per second. So if we say, it's at the next part of the question says, how much work is done on the battery in 5 minutes? If we have 144 joules per second, and we have 5 minutes, we know that 5 minutes, if we were to convert that in 1 minute, there's 60 seconds. So that would be 300 seconds. So put that in down here, 300 seconds. We would do 144 times 300, gives us 43,200 joules. So the answers I'm going to go with for A, how much current? Looking at 3 significant digits, we got 3.0 amps. For B, how much power? We have 140 watts. And C, for work in 5 minutes, we're going to have 43,000 joules. Okay? Came up with 3 answers there. Let's move on to our second question. It says, a very reckless, foolish daredevil puts his ear on the rail of a railroad track and saw the steam from the whistle of the train 4 1,400 kilometers away. I'm exaggerating a little bit. You can't see a train coming at you 1,400 kilometers away. But this guy isn't as foolish as the guy the other day who was 1.4 kilometers away. This might be a little bit safer experiment if he was doing that. And it says that he's got this copper rail. Yesterday we were working on iron. Today we got copper. So here's the railroad tracks. And in our free body diagram, we'll put a train. And then we have our foolish person. There's the train. He sees the steam coming off the train. And he lays down on the track to listen to the sound of the rail. So if I were to look at this, I'm going to start with the distance away, 1,400 kilometers. And I want to calculate the time it takes in the air. So we got 1,400 kilometers. A kilometer is 1,000 meters. And in the air, we are told that the speed of sound is on average 350 meters per second with a little bit of leeway there. So now that would cancel out our meters and cancel our kilometers. The only thing left is seconds. So we do 1,400 times 1,000, which gives us 1,400,000. Then we're going to divide by 350. And we have, it would take 4,000 seconds for the sound to get there. That's quite a while. I'm guessing it's not going to reach your ears, that sound. But anyways, now we want to find out if he were to put his ear on the copper rail, how long would it take for that sound to get there? So we'll start with 1,400, and we're going to look at copper here. 1,400 kilometers. 1,400 kilometers. A kilometer is equal to 1,000 meters. Now, see, I want to get rid of my meters, but this is where I come up with a problem. How do I know what my formula unit is going to be? It's not given in the problem. I gave you a chart, speed of sound in various mediums that you should have available for you. This was in problem set 35's lesson, and so that should be available for you. And when I look it up, I find out that copper is 3,750 meters per second. So it has a speed of, the sound travels in it 10 times faster than it does in air. So as we calculate this, we got 1,400 times 1,000. Again, gives me 1,400,000. Then we're going to divide by 3,750. And we have 373.3 repeating seconds that it takes for it in copper. So the clear winner, if you're going to hear it faster, is the copper than the air. So when it comes up to my answers, which did you hear it first? Well, we heard it in the copper. Cu, is the symbol for copper on the periodic table. And in Cu, the time for each, and we had 2 significant digits in the problem, so it was 370 seconds. And in the air, it was 4,000 seconds. Now, how do I denote 2 significant digits? I'm going to put a line over the zero, the first 0 in 4,000. All right, does that make sense? I hope so. Let's move on to the next question. This one we get a little more complicated. It says we got a 105 kilogram block that sits on a level floor. And the coefficient of kinetic friction is 0.567. A horizontal force of 621 newtons is applied to the block for 7 seconds. Use Newton's second law to calculate the acceleration of the block. Find the total impulse of the block using momentum. So it kind of spells it out. I know this isn't necessarily a problem that we've worked on specifically. So we just need to kind of read what's going on. So the first one says Newton's second law. So we go Newton's second law. hopefully after years of teaching these laws to you, you know that it's the sum of the forces in any direction is equal to mass times acceleration. And then it says impulse momentum. The impulse momentum is calculated by, hopefully you know this too, fat MAV. All right. So it says use Newton's second law. So I'm going to put my box here. And we'll begin looking at the forces. We have 105 kilograms. That's heading down. So you got force normal heading down. And then you have the force of 621 newtons heading that direction, which we call F of x. And F of k heads in the opposite direction. And we have a coefficient of kinetic friction of 0.567. All right, so if Newton's second law says force equals mass times acceleration, I know I have positive Fx minus Fk equals mass times acceleration. I need to calculate Fk. Fk is found by force normal times the coefficient of kinetic friction. Force normal will be calculated by multiplying 105 times 9.81. So if we have 105 times 9.81, we get 1030.05. So then we'll take that 1030.05 and we'll multiply that by 0.567 to get Fk. So Fk will equal times 0.567, 584. Wow, those are some very, very close numbers we're going to end up with. Okay, so let's sum our forces. So Fx is 621, Fk is 584, and that equals the mass, which was 105, given to us in the problem, and times acceleration. So 621 minus 584, and I'm actually using like 584.038 or whatever. So we get 36.96 equals 105A. So then we'll divide by 105, and we'll get our acceleration being positive 0.3520 meters per second squared equals acceleration. So then if I were to continue looking on, the next thing I want to do is I want to find find the total impulse of the block. Well, the impulse will be the net force times the change in time is the impulse. Got that from right there. So the net force is found right here. Just so you know, the net force is 36.96 times the change in time. That's how this problem is kind of different from stuff that we've done earlier this year, because we're looking at the net force. A lot of the problems we used already had a frictionless surface. So this kind of changes things. So we have 36.96 times the 7 seconds gives me my total impulse of 258.72 Newton times seconds. All right, and so then it says now take your momentum into the equation to find the velocity. All right, so we know that impulse that we just found, 258.72 equals the momentum, which is the MAV part. So over here we're going to begin using the MAV. So the mass is 105, and that'll allow us to find the change in velocity after those 7 seconds. So divide by 105, and we'll get 2.464 meters per second equals the change in velocity. So now if we think about it, Like it said we had to use the momentum, but if we were to think about accelerating for 7 seconds, if we took 0.3528 and we want to check our work, we'd multiply that by 7 seconds. So if you took that number and multiplied by 7, you're going to get 2.46 again. Actually, because of rounding that I've done along the way, it's a little bit different. It's the answer I came up with is 2.4696. So it actually ends up looking a little bit different because of surrounding errors. That's why we need to go back to significant digits. There's two significant digits in the problem right here. So when I come up with my solution, A, it says find the acceleration, 0.3535 meters per second squared. For B, it says find the impulse. So the impulse is going to be 260 Newton seconds. And C, it says find the final velocity, 2.5. Now, no matter what rounding rule I'm using, I'm getting the same thing. So, like no matter how much both times I rounded, I'd get the same answer, even though they're a little bit different. So, okay. All right. Now we got one more problem, I believe, that we're working on, and this is a combined gas law problem. Now, a few weeks ago, I believe, we said combined gas law says PV over T equals PV over T. That's combined. Now, on that, I said there are number of laws. There's Boyles, there's Charles, and there's Guy-Lussac's or Guy-Lussac's. I heard it pronounced that way the other day. So, which one, it asks in this question, whose law, which one of these three guys does this question represent, and describe the relationship. So let's work on all that. So it says Susan had a gas in a container. The pressure initially is 202,000, right? Yep, 5 significant digits, pascals. That's P1, okay? Then it says it was increased to 3, oh, that's not increasing, that's decreasing. It was decreased to, I'll have to go back and change that. It was decreased to 34,000 pascals. If you read what it says here, to the 5th power, and then it goes down to the 4th power. So it's actually decreased. So pressure 2. And it says the initial, or V1, equals 7.1 cubic meters. We got to find V2. Now there's no mention of temperature, so I'm going to believe that that means temperature is constant. Now I know it's not specifically stated, but since it's not stated, we're going to assume that. And with the idea that it's got to be one of these three guys' gas laws, we got to figure that out. So if we set this up, T remains constant. So as I begin to solve, we can eliminate T. So we got P1V1 equals P2V2. So P1 is 202,000 times V1 of 7.1 equals P2, which is 34,000, times V2. So we'll take 202,000 and multiply by 7.1, and I get 1,434,200 equals 34K V2. So we divide by 34,000, and we get 42. And since it's 2 significant digits, I could go on. It's like 42.18235. But 42 meters cubed equals my final volume. So what happened to the volume? I'm guessing if you look carefully, you'll see part A says that V2 is 42 meters cubed. The next thing says, whose law does that illustrate? Well, if you go and you look at the different laws, you'll find that there's Boyles Law, Charles Law, Guy Lussick's Law, and hopefully you've been looking at these so you can kind of tell the difference between them. This specifically is Boyles Law, PV equals PV. So part B is Boyles Law. Now it says describe the relationship. So here, if I were to put together a graph of what's going on, and the first thing I had was pressure. So I'm going to make that my X. So pressure. So our pressure goes up, or excuse me, our pressure goes down. So that means it's going this direction. Okay. So as our pressure goes down, so we're going backwards, what happens to our volume? So we went from 202,000 to 34,000. That's what happened to our pressure, right? We went from 202,000 to 34,000. So at 202,000, it was at 7.1. When we got to 34,000, we went up to 42. So if I look at the graph, as one went down, the other one went up. So this one went down while volume, if we were to compare volumes here, volume went up. So they went in opposite directions. That means that we would call the relationship an inverse variation. You guys have worked on in math class, in Algebra 2, in pre-calc, you've spent some time working on this important thing. A lot of colleges are looking at this and saying, so you understand the concept between direct variation and inverse variation is very, very, very important. If one goes up, the other one is going to go down. That's kind of a concept that's going to, maybe you won't work on gas laws your whole life, but even if you're in economics, if you're in engineering, one of the things that's good to know is if one goes up, the other goes down. It's called inverse variation. Whereas if they both go up, is direct variation between the two, and things can also be jointly varied. So this is a good concept to teach that on. All right. Well, thank you so much for sticking with me through that video. Hopefully you learned some things to help prepare you for Friday's test. These inks will be posted on the website. Have a good day.